Today, we're diving into a puzzle at the very heart of matter. We're going to a place where, believe it or not, 1 plus 1 just doesn't seem to equal 2, and where the basic math we all learn in school kinda falls apart.
I mean, this is a question that completely baffled scientists for years. You'd think if you took an atom, weighed all of its individual parts, and then weighed the whole thing, the numbers should match up, right? Well, they don't. Something is missing. And this is it, the core fact that drives this entire mystery. It just feels wrong. It's like saying a car weighs less than its engine, wheels, and frame all put together. But, down in the quantum world, this is the strange reality. Okay, let's stop talking in hypotheticals and get specific. To really see what this missing mass actually looks like, we need to pick an atom and put it under the microscope. So let's meet our subject, a stable, run-of-the-mill helium-4 atom. It's super common and pretty simple. It's got 2 protons and 2 neutrons hanging out in the nucleus, and then 2 electrons orbiting around them. Seems straightforward enough. All right, now it's time to do the math. Let's put on our atomic accountant hats and add up the mass of every single piece just to see what this helium atom should weigh based on its parts. First up, the 2 protons. Using the standard unit for this, the atomic mass unit, or U, their combined mass comes out to this number right here. Next, we add the 2 neutrons. They're just a tiny bit heavier than the protons, adding another chunk of mass to our total. And finally, we can't forget about the 2 tiny electrons. I mean, their mass is practically nothing, but hey, for the sake of being precise, we'll add that little bit in too. And here's where it gets weird. When we add all those parts together, our grand total is 4.032979 U. But, and this is the kicker, when scientists actually put a whole helium-4 atom on the scale, it weighs less. The whole is literally lighter than the sum of its parts. So this difference, this phantom weight that has just vanished, is 0.030377 atomic mass units. Scientists have a name for this. They call it the mass defect, and it is the key to our entire puzzle. So where did it go? Did it just disappear into thin air? Were our calculators broken? Nope. The answer is so much more profound, and it unlocked one of the greatest secrets of the universe. The big clue to solving this whole thing comes from a mind that completely reshaped how we see reality, and from an equation so famous, I bet you already know it by heart. Yep, E equals mc squared. Albert Einstein's incredible insight showed us that there's this hidden, unbelievable relationship between energy, or E, and mass, m, and they're forever linked by the speed of light squared. What this equation is really telling us is that mass and energy are, fundamentally, interchangeable. They're not totally separate things, they are 2 sides of the same cosmic coin. You can convert a little bit of mass into a tremendous amount of energy, and you can even turn energy back into mass. So, how does this solve our little mystery? Well, that missing mass from our helium atom didn't just vanish into the void, it transformed. So, to just officially define it, the mass defect is exactly what we calculated. It's that tiny slice of mass that seems to go missing whenever an atom is built from its component parts. And here is the solution. That tiny bit of missing mass was converted into an immense amount of energy, what we call nuclear binding energy. It's basically the cosmic glue that holds the atom's nucleus together, fighting back against the powerful forces trying to push those protons apart. And look, this isn't just some abstract idea on a chalkboard. This binding energy has huge, world-changing implications. Whether we are splitting a heavy atom apart, that's fission, or smashing light atoms together in fusion, what we're really doing is messing with this binding energy. Releasing just a tiny fraction of it is what powers everything from nuclear reactors right here on Earth to the stars themselves. And this image, this shows that power in action. What you're looking at is high-temperature plasma, a state of matter so incredibly hot that electrons are just ripped away from their atoms. Learning to contain and control this stuff is the whole key to harnessing nuclear fusion, to unlocking the very same process that fuels our sun. So, from the fiery hearts of distant stars to our most advanced laboratories on the planet, humanity's greatest scientific quests are all, in a way, about understanding and unlocking the incredible power that's hidden inside that tiny, tiny bit of missing mass. So to recap our whole journey, we started with what looked like a simple accounting error inside an atom. That mystery led us to Einstein's world-changing equation, which revealed that the missing mass had actually become the energy that glues the nucleus together. And unlocking that energy? Well, that's the power source of the entire universe.
It's a pretty wild thought. A puzzle that started with the tiny little number that didn't add up ended with the energy source of the stars. It really makes you wonder, what other profound secrets are still waiting for us, locked away in the places we can't even see?